In this video, I'd like to talk about the math question of the day for Sunday, April 16th, 2023. And with this problem, we need to determine the length of this curve between y values of 189 and 875. And since we're finding the length of the curve, we need to understand the concept of arc length and how to find that using calculus. And this is generally a topic that is taught in Calculus 2. So to answer this question, you do need to have a solid understanding of both Calculus 1 and Calculus 2, as well as everything that comes before that. So at this point, go ahead and pause the video, see if you can work through this on your own, and when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through this. And admittedly, this is a fairly challenging problem, not only because we need the tools of calculus, but because we're given a function in terms of the variable y, but we're also given the bounds in terms of y as well. So to find the length of this curve, let's first get a visual of what this curve looks like, and in particular, look at the section we are concerned with. So let me show you that on Desmos. I just quickly plotted this curve. And we can see the curve here in red. And we can see the lower bound, that's in blue, at y is equal to 189. And the upper bound is this green line, y is equal to 875. So our concern in this problem is to find the length of this curve between the blue and green lines. So this will just give us a visual for exactly what we're trying to find. But let's go back to the blackboard and we can start working through this. And before we consider this specific problem, let's just think about arc length in general, since it can be a little bit confusing. If you know the formula for this, you can just apply the formula. But understanding where the formula comes from can be a little bit difficult. So let's say we have some curve. We can call this f of x, our function here. And let's say we're concerned with a specific interval, let's say between x values of a and b, or we can even consider the y values, since sometimes that's more useful. Let's say it goes between y values of c and d in this case. And again, what we're trying to find is just the length of this curve between these two endpoints. And the general process is to split up our curve into tiny pieces and focus on those. So let's say we're looking at a small piece of our curve there. And let me zoom in on that. Let's say it is right here. And if we zoom in far enough, let's say at this point right here, if we zoom in close enough, the curve will resemble a straight line. And I will exaggerate this. We're going to be looking at a very tiny section of the curve. We'll be using differentials here. Let me make this a little bit clearer. But just so that we can visually process this, let's make it a little bit bigger. And we can call this tiny length of curve delta s. And what we're effectively doing is taking our interval and splitting it up into an n number of pieces. And we can focus on x or y, it doesn't matter, but let's look at delta x. That would be the horizontal component of this. And then delta y would be the vertical component of this. So we can take our little piece of arc length here, which we call delta s. We usually use s for arc length. And we can deconstruct it into a right triangle, where the horizontal component is delta x and the vertical component is delta y. And like I mentioned, we're essentially taking this interval here and splitting it up into n number of pieces, so that if we want to be a little bit more precise about this, delta x would be that entire interval here, but split into n pieces. And then we will apply limits and calculus to this. And this won't be a completely rigorous proof of this, since that will take a little bit longer. But at this point, we can take a limit and let n approach infinity. And we essentially can shrink down this tiny little section we're looking at so that it becomes a differential. In some sense, it becomes infinitely small, but again, that's not necessarily the rigorous way to look at it. So when we go back to our curve here, instead of having delta s, when we actually take this limit, and again, I'm going to exaggerate this so that we can actually visualize it. Now we're dealing with ds, the differential for this arc length. But again, we will be able to deconstruct that into a triangle. And let me do it on this part so that we can actually visualize that triangle, where the horizontal component is now dx. After taking this limit of delta x, it just becomes dx. And our vertical component is dy. But we have this triangle where we can relate the three sides by using the Pythagorean theorem. ds squared is dx squared plus dy squared. And the entire purpose of looking at one little section of this curve is that if we know the length of one section, we can then just add up all of the tiny little sections along the curve. And again, I am exaggerating the size of these. These would be extremely tiny, but you can get the idea that we're just going to add all of those up. So we can say that L, this is the arc length of our curve. This is the integral of ds. And the bounds could be from a to b, or they can be from c to d, depending on how the function is written. So before we put bounds in, let's manipulate the formula for ds. If we take a square root of each side, we'll solve this for ds. And we can rewrite that L is this integral of ds, but ds is really the square root of dx squared plus dy squared. And we can do a little bit of algebra here. Inside the square root, we can factor out either dx squared or dy squared. But let's start by doing it with dx squared. So we have the integral of the square root of dx squared. And we factored it out from here, so we have 1. And factoring out from here, we will end up with dividing by dx squared, since if you remultiply this out, you get back what you started with. And since we have a product, we can take the square root of each of these, and the square root of dx squared is just dx. So we end up with a dx on the outside of the square root, and on the inside we have 1 plus dy over dx squared. And this quantity here, this is just the derivative of our curve with respect to x. Now, I did mention we can also follow the same process, but with dy, and I won't go through all of it, but basically we end up with a very similar expression. We have 1 plus dx over dy, and we square that, and the dy is now on the outside. And this just allows us to write this integral in two different ways. If we write it in terms of x, or dx on the outside, then our bounds will be from a to b. But if we write it in terms of dy, then it goes from c to d. And that is really just dependent on how the function is given to us. Since our function is given in terms of y equals, it's solved for y, it will likely be best to rewrite our bounds in terms of x. Even though they're given in terms of y, it will be simpler to rewrite the bounds rather than to try to solve this equation for x and then use these y bounds. But if you want to try that, you can certainly take that approach as well. So with these, we have two different choices. And for our specific problem, we will rewrite the bounds in terms of x, and we just need to find the derivative of this curve y with respect to x, and then we can just use this formula here. And again, this is not a completely rigorous proof, but it should give you a good intuition for where this formula comes from so that you don't have to completely memorize it. Understanding the derivation of a formula is often just as important as the formula. So let's make a little bit of room, and we can apply this formula. Again, we're using the formula where we have dx rather than dy. And because of that, we will need to find the x values such that y is equal to 189 and 875. So let's start with that. Let's change our bounds first. For 189, we will just plug that in for y, and we just need to solve this for x. We need to perform a little bit of algebra here. We can start by dividing each side by 7, so that we get 27 is 6 plus x to the 3/2 power. We can take a cubed root of everything so that we can cancel out the 3 and the numerator here, so that this just becomes a square root. Since 27 to the 1/3 power, that's just 3. So we get 6 plus x, now raised to the 1/2 power. Let me delete that. And to get rid of this square root here, this raised to the 1/2, we just square each side. So we get 9 is 6 plus x, and subtracting 6, we get that x is 3. So that is one of our bounds. That's for this lower y value. And for the upper y value, we will apply the same process. We'll plug in 875 to this curve where we see y. And we can start by dividing everything by 7 so that we get 125 is 6 plus x to the 3/2. We will again raise everything to the 1/3 power, so we're taking a cubed root of everything. And on the left, we just get 5. On the right-hand side, we lose the 3 in the numerator. It just becomes a 1 now. Same process as above. And to get rid of the 1/2 exponent, we square everything. So we get 25 is 6 plus x. And subtracting 6, we get that x is 19. So we have the bounds, and now we just need to apply this formula. But to do that, we need to find this quantity here, which if we wanted, we could just write it, if this was our function f of x, you might see it f prime of x, and we are squaring it. So sometimes you'll see that, though honestly this notation's often a little bit clearer for what we're actually doing here. So let's take our curve and find its derivative. Let me take a picture of this and we'll work down below. So let me just make a little bit of space here, and we can keep using our formula. And let me paste in the picture of our curve here. And again, we just need to find its derivative. And that derivative needs to be taken with respect to x. So let's do dy dx. And we'll use the power rule. We can take our exponent, bring it down in front, so that we have 7 multiplied by 3/2 multiplied by 6 plus x, and we subtract that by 1, so that we have 1/2. And we would then multiply by the derivative of the inside, but that's just 1. So that's using the chain rule here. So let's simplify everything. We have 21 over 2 multiplied by 6 plus x to the 1/2 power. Now notice in our formula we have to square this. So let's do that first before we actually plug it in, since this will get a little bit messy. We have 21 squared, which is 441. 2 squared is just 4. And we're squaring this expression, so the square root, this 1/2 power, will cancel out, and we actually just get 6 plus x. So that's a nice simplification. And if we want, we can distribute this and clean this up a little bit. If we distribute the 441, we get 2,646. And we have 441 multiplied by x, and then all of this is divided by 4. So that's this expression, and then we have to add 1 to that. So let's start working on this arc length formula. We have that L, the arc length, goes between x values of 3 and 19, which we figured out above. And then we have the square root of 1, which I'll write as 4 over 4 so that we can combine it to this fraction, plus 2646 plus 441x, all divided by 4. And we'll need to simplify that, so let me make some room so that we can keep keep working. We also have dx on the outside. And we'll rewrite the bounds. We add 4 to this expression here on the inside. We still have our square root. We have 2,650 plus 441x. All of this is divided by 4, and we have dx. And since we have a fraction, we can take the square root of the top and the bottom, which will simplify that denominator. This will just become 1/2, which we can factor out. Put that on the outside. And this remaining integral, since it's a linear function, we can use u substitution to simplify everything. So let's set u equal to 2,650 plus 441x, and when we take its derivative, we just get 441 multiplied by dx. So if we divide each side by 441, we have that du over 441 is equal to dx, and we can substitute that in right now, and this will just become the square root of u. So let's make more room here. This is quite a lengthy problem, but we are getting close to the finish here. This 441 will actually just come on the outside and will be in the denominator. So we have twice that, which would be 882. Now our bounds will change, but I will leave the bounds until the end. We will substitute this back in for u, or we can just figure out what the bounds are in terms of u. So that's a personal choice, but we end up with the square root of u multiplied by du, though let's write this as u to the 1/2 power so that we can apply the power rule for antiderivatives. And this will become 1 over 882, and we get u to the 3/2 power divided by 3/2, but let's put it back in terms of x. So we'll plug this back in for u. 2650 plus 441x, all raised to the 3/2 power. We're just adding 1, and then we're dividing everything by 3/2. So after a little bit of further simplification, and I should put in the bounds here, we're going from 3 to 19. We can simplify with some arithmetic out front so that we just get 1 over 323. And we have this expression on the inside, 2650 plus 441x, all raised to the 3/2 power, and that's between bounds of 3 and 19. Now, at this point, it is entirely arithmetic. We will plug in x equals 19. We will multiply that out, add these together, and then raise it to the 3/2 power, and then multiply it by this fraction, and then we will subtract when x is equal to 3. Again, we will just go through all that arithmetic again. So if you've made it this far, I'm not going to go through all of that arithmetic. I encourage you to check that on your own, but if I paste in the final answer, this would be the exact expression after plugging in 19 and adding these two terms together. We would get 11,029, all of that's to the 3/2 power, and we're subtracting when x is equal to 3. Again, plug that in, add these together. We get 3,973 raised to the 3/2 power, and then all of that is multiplied by this fraction in front. And if you do want it as a decimal, this would be our approximation here. So this number right here, this is the length of that curve. If we go all the way back up to that original curve here, we found the length of this curve between y values of 189 and 875.